So on December 31st, 2024, uh, a Nobel laureate passed away, leaving behind this incredible legacy of microscopic machines.
Right, Sir Fraser Stoddart.
Exactly. And then on that exact same day, a yoga therapy teacher from Jerusalem published a paper that, well, it basically turned those classical molecular machines into quantum computers.
Yeah, the timing alone is just, I mean, it's one of the most astonishing coincidences in the history of science, really.
It really is. Like, if you're listening to this and wondering how, a wellness practitioner out-theorized Ivy League physics labs, the secret lies in this completely mind-bending crossover between human biology and quantum mechanics.
Which is wild because the author, Yehudah Shilo Groskin, he wasn't a tenured professor with, like, a billion-dollar lab.
Oh, no, not at all.
He was an independent researcher. Hours after Stoddart passes away, Groskin drops this paper on Zenodo, which is an open access repository.
Right, and it was titled Seamless Evolution of Molecular Machines to Quantum Coherence, which sounds super intimidating.
It does, yeah. But what makes the rigorous peer review happening around this paper today so fascinating is that he didn't just write, a philosophical essay.
No, he dropped a dense, mathematically bulletproof framework.
Exactly. He took Stoddart's entire life's work, these physical, moving, molecular parts, and forced them to operate using the teleporting, probability-based rules of the quantum realm.
Which is just crazy. So for you listening today, in this deep dive, we are going to unpack exactly how Groskin built this bridge.
We're going to look at the underlying math.
Yes, the math and the incredibly surprising biological fuel used to keep the whole thing from falling apart. And ultimately, why this independent paper might literally be the blueprint for the future of computing.
Right. But to really appreciate the leap Groskin made,
Right.
I think we have to ground ourselves in what Stoddart actually spent his life building.
Yeah, let's start there, because Stoddart fundamentally changed how we view chemistry.
He did, because for centuries, chemistry was mostly about static architecture.
Like things just sitting there.
Exactly. You bond atoms together, they share electrons, and they basically just form a structure and stay put.
Right. It's like building with tiny Lego bricks that snap together and don't move.
That's a great way to put it.
Yeah.
But Stoddart introduced mechanical bonds. He created mechanically interlocked molecules, or MIMs.
Okay, MIMS.
Yeah, think of rotaxanes and catenanes. These are molecules linked like interlocking rings on a magician's chain.
Oh, wow.
Or, like a tiny microscopic ring threaded onto a chemical axle.
So they aren't glued together by sharing electrons?
No, they are physically trapped together, but they can still move independently.
So he essentially built the world's smallest physical machines.
Exactly. He made molecular switches, tiny elevators that go up and down an axle, even artificial nanoscale muscles.
That is just wild. But the key here is that they are physical, right?
Yes, completely physical.
You have these classical molecular machines that click into place and do actual physical work. They obey the standard rules of classical physics, just scaled way down.
Right. And Groskin looks at these classical switches and asks, well, what happens if we manage their dynamic phase transitions so they process information at a quantum level?
Which is a monumental hurdle. I mean, let's be real.
It's massive. Groskin isn't just trying to make the molecule move from point A to point B.
Right.
He wants these machines to exist in multiple states simultaneously quantum superposition, so they can actually act as qubits for computing.
I want to really visualize the paradox here because it feels like taking a traditional mechanical grandfather clock with all its physical moving brass gears, right?
Okay, yeah. That's Stoddart's work in this analogy.
Right. So Groskin is proposing that we don't just let those physical gears push against each other mechanically. He wants them to be entangled, operating in like a probability cloud.
Yes, exactly.
But physical gears and quantum states are entirely hostile to one another. If I try to make my grandfather clock vibrate in a quantum superposition, the whole thing falls apart.
It would just shatter. Yeah.
The physical friction, the sheer mass of the gears, it destroys any quantum state. You can't just, wish a classical machine into a quantum superposition.
You absolutely cannot. You need a mathematical bridge before you can even dream of a physical one.
Right.
And Groskin provides that in the paper with the unified Hamiltonian derivation.
Okay, let's unpack that without losing the plot because Hamiltonian sounds heavy. In physics, a Hamiltonian is essentially the ultimate accounting ledger for a system's energy, correct?
That is a perfect way to describe it. It's the master equation.
Okay, cool. So it describes the total energy environment so we can predict how the system behaves.
Exactly. And if you want to unify two completely different physical regimes, they absolutely have to share a Hamiltonian.
So Groskin builds a total system energy ledger that combines the classical world and the quantum world.
Yes. The first half of it is the mechanical energy. This tracks the classical physics, the literal kinetic energy of the moving molecular rings, and the potential energy of where they are located on their axle.
So the mechanical side is tracking the mass and the velocity. It's tracking the swinging pendulum of our grandfather clock.
Precisely. And then the second half is the quantum energy.
Okay.
Groskin represents this using quantized harmonic oscillators.
Hold on, let's unpack quantized harmonic oscillators for anyone who doesn't have a physics textbook open right now.
Sure, yeah.
A harmonic oscillator is basically something that swings back and forth like a pendulum or a spring, right?
Yep, exactly.
But quantized means it can't just swing at any random speed. It's like a guitar string that can only vibrate at specific, defined frequencies.
That is the crucial distinction, yes. Because in the quantum realm, energy isn't a smooth ramp.
It's more like a staircase.
Exactly. It's a staircase. You can only step on specific stairs. The math Groskin uses here involves what we call creation and annihilation operators.
Which sounds like something out of a sci-fi movie.
It really does. But simply put, these are just mathematical tools that describe adding a specific packet of vibrational energy to the system or taking one away.
Okay, so we have the classical accounting on one side of the ledger, the physical gears,
Right.
and the quantum accounting on the other side, the discrete vibrational stairs. But just putting them in the same equation with a plus sign doesn't mean they actually talk to each other.
No, it doesn't.
Like, I can write down an equation that adds the speed of my bicycle to the temperature of the sun, but pedaling faster doesn't cause solar flares, you know?
That is very true.
There has to be a mechanism that links them.
Which is why the third piece of Groskin's equation is the actual breakthrough.
Okay, what is it?
He introduces a coupling term.
A coupling term.
Yeah. This mathematical handshake explicitly dictates how the physical location of the machine affects its quantum state and vice versa.
But how does that actually work on paper? I mean, how do you multiply a physical distance by a probability cloud?
So the coupling term takes the mechanical displacement, literally the physical XYZ coordinates of the molecular ring on its axle.
Oh.
And it mathematically intertwines it with those quantum creation and annihilation operators we just talked about.
Oh, wow.
He uses a specific coupling constant, which is denoted as G. And this acts like a volume dial.
A volume dial.
Yeah. It dictates how strongly the physical movement influences the quantum vibration. Groskin didn't just theorize that they should interact. He wrote the exact algebraic formula proving how a physical nudge translates into a quantum ripple.
That is just, it's mind-blowing. So we have a unified equation that proves, at least theoretically, you can couple a physical Stoddart machine to a quantum state.
Yes.
But, and this is a big but, any physicist reading this paper is going to immediately hit the panic button over the decoherence problem.
Oh, absolutely. It's the eternal enemy of quantum computing.
Wait, hold on. I need to push back hard on this because this is where the paper's claims start to sound like complete science fiction to me.
Fair enough. Go ahead.
Quantum states are famously fragile. They are like a house of cards balancing in a hurricane.
Yes, they are.
To build a traditional quantum computer today, companies like IBM have to place their chips inside massive liquid helium refrigerators to cool them down to a fraction of a degree above absolute zero.
Right, the dilution refrigerators.
Exactly. And they do that because any ambient heat is just atoms vibrating, right? That thermal kinetic energy crashes into the fragile quantum state and destroys the superposition instantly.
The quantum wave function collapses.
Yes, sorry. I mean, the system just reverts back to normal, boring, classical physics.
Right, it loses all its quantum properties.
So if Groskin is proposing we run these molecular quantum machines in real-world biological environments, I mean, that is a boiling cauldron of thermal noise at the nanoscale.
It is. It's incredibly noisy.
How does his math possibly cancel out literal heat?
Well, this is where Groskin pivots from physics into biology.
Okay.
And this is exactly where his background in wellness and human physiology clearly influenced his thinking.
Really?
Yeah. He introduces the Unified Balance Theory formula, or UBTF.
UBTF, got it.
He proposes that you don't actually need liquid helium to protect the quantum state, not if you use a biological shield.
A biological shield.
Yes. And the fuel he uses for that shield is ATP adenosine triphosphate.
Wait, ATP. The exact same biological molecule that acts as the energy currency in our human cells.
The very same.
The stuff my muscles burn when I go for a run.
You are saying he uses cellular muscle fuel to stabilize a quantum computing state.
I know it sounds absurd until you look at the mechanism.
Yeah.
Groskin's model creates what he calls an effective temperature that is modulated by the concentration of ATP.
But how does a molecule mimic the freezing temperatures of absolute zero? I mean, ATP doesn't magically absorb heat and turn its surroundings into a freezer.
No, it doesn't cool the room down. Think about what ATP actually is structurally.
Okay.
It has a tail of 3 phosphate groups, and the bonds holding those phosphates together are packed with immense potential energy.
Right. And when those bonds break, they release energy.
Exactly. Groskin's framework suggests that the energy field created by a high concentration of ATP acts as a dampener. Oh, wait, is it like a acoustic foam in a recording studio?
I mean,
Well, if the ambient heat of the environment is like loud traffic noise outside the studio noise that would completely ruin the fragile quantum song being played inside, do the ATP molecules surround the quantum machine and act like foam panels?
that is a phenomenal analogy. Yes, exactly.
No way.
The ATP acts as a chemical shock absorber. So when thermal energy, those random heat pumps, hits the system, the dynamic chemical environment created by the ATP intercepts and dissipates that specific kinetic interference.
So it effectively mutes the thermal noise.
Yes, the quantum machine inside doesn't even know it's sitting in a warm room.
Because the ATP has created an isolated, buffered pocket where the effective temperature feels close to absolute zero.
Exactly.
That completely flips the paradigm of quantum computing.
It changes everything.
Instead of mechanically freezing the entire room to kill the noise, you just put noise-canceling headphones on the molecule itself using biological chemistry.
Yeah.
Does the paper actually quantify how well these noise-canceling headphones work?
It does, in great detail. Groskin details specific decay rates.
Okay, what are the numbers?
So without ATP, the quantum coherence falls apart rapidly, with a base decay rate of 0.5 per minute.
Fast.
But he introduces an ATP modulation factor into his math. He calculates that introducing a high concentration of ATP suppresses that decay.
So the ATP literally delays the collapse of the quantum state.
Exactly. It buys the system time to process information.
Okay, but math on a chalkboard doesn't mean much if the biological fuel just burns up when you actually test it in the real world. Did he run simulations to prove this ATP shield holds up?
He did. The paper details incredibly rigorous experimental methods and numerical simulations to back up all the math.
Wow, okay.
Groskin used Python and MATLAB to run the numerical simulations, and he validated the analytical results with symbolic computation tools.
But if he's testing ATP, he must have run this at a biological temperature, right? Because if you freeze ATP to absolute zero, it just becomes a useless block of ice. It only functions in a liquid warm state.
You've hit on the exact parameter that makes this paper revolutionary. The simulations and the experimental environment were strictly controlled at 37 degrees Celsius.
37 degrees Celsius. Wait, that's 98.6 degrees Fahrenheit?
Yes.
Human body temperature? He ran a quantum computing simulation at body heat.
He did, using a highly precise thermal regulation system, like a PID feedback system, to keep the temperature perfectly stable.
That is unbelievable.
And then he introduced ATP solutions ranging from low concentrations of 0.1 millimolar up to high concentrations of 5.0 millimolar.
Okay, but if he's doing this at body temperature, he still has to deal with the quantum spins of the atoms wandering off and losing alignment, right?
Was he using a magnetic field to keep them pointing the right way?
Spot on. He applied a continuous magnetic field between 0.5 and 2.0 Tesla. Okay, which makes total sense. The magnetic field acts like a corset, holding the quantum spin states rigidly aligned,
Yes.
while the ATP acts as the acoustic foam shielding them from the thermal heat.
Exactly. It's a two-part defense system.
So, with the magnetic corset on and the biological ATP foam in place at human body temperature, what happened? I mean, when did the quantum state finally die?
So the paper tracked the exact moment of the phase transition, the moment the system loses its quantum coherence.
Okay.
At low ATP concentrations, around 1 millimolar, the acoustic foam just wasn't thick enough. The quantum coherence collapsed in about 2 minutes.
I mean, 2 minutes at body temperature is still a staggering achievement in quantum physics.
It really is. But wait till you hear what happened when they flooded the system with fuel.
Okay, what happened?
At high ATP concentrations, 5 millimolar, the coherence was drastically sustained. The collapse was delayed all the way to 6 minutes.
6 minutes?
Yes. By quintupling the biological fuel, he effectively tripled the lifespan of the quantum state in a warm environment.
That is insane.
And the simulation trends matched the preliminary experimental data perfectly, which validated the entire unified balance theory formula.
The paper mentions a specific trigger point for this collapse, right? A critical threshold of zero point 0.8 normalized amplitude.
Yes, that's correct.
I want to visualize this moment of death.
Uh-huh.
When the system hits that zero point 0.8 threshold at the 6-minute mark, does the Stoddart molecular machine physically shatter?
Not at all. The mechanical integrity of the machine is totally unaffected. The interlocking rings, the rotaxenes, they don't break.
So the physical hardware survives?
Yes, completely.
Yeah.
Hitting the zero point 0.8 threshold simply means the acoustic foam has failed.
Ah, okay.
The thermal noise finally breaks through, and the system loses its quantum superpowers. It instantly stops existing in a superposition. The entanglement dissolves.
So the machine just reverts back into a classical physical Stoddart molecule.
Exactly.
The grandfather clock just stops teleporting and goes back to ticking normally.
Precisely. And the fact that Groskin proved we can predict and chemically control exactly when that transition happens using the fundamental energy currency of human life.
Yeah.
I mean, it alters the trajectory of several scientific fields.
If we zoom out and look at the implications of this, I mean, this isn't just an abstract physics puzzle. We're talking about the foundational blueprint for biological quantum hybrid computers.
Absolutely. We're talking about a completely new frontier.
Because for decades, we've assumed the future of computing looks like sterile silicon chips locked in sub-zero industrial refrigerators.
Right. Massive machines in freezing rooms.
But Groskin's work points to a future of wetware. Computers that use the mechanical architecture Sir Fraser Stoddart invented, operated by the quantum equations Groskin derived,
Yes.
and powered by the exact same biological ATP currently pumping through your own heart.
It is the literal definition of a living evolution in science. Stoddart spent a lifetime building the physical chassis, right? The nanoscale gears and elevators.
Yeah.
And now, researchers are learning how to breathe quantum processing power into that chassis, using the chemistry of life itself as the stabilizer.
It's an incredible narrative arc. I mean, we started this deep dive looking at a deeply cinematic moment. December 31st, 2024, a titan of chemistry passes away.
Okay.
And on that very day, an independent researcher, a yoga therapy teacher, no less drops a mathematically rigorous paper on Zenodo that pushes the laureate's physical machines into the quantum universe.
It's almost poetic. We walk through how Groskin bridged that gap. He didn't just guess. He derived a unified Hamiltonian mathematically linking physical displacement coordinates with quantum vibrational states.
And we saw how he completely circumvented the need for absolute zero temperatures. Instead of freezing the system, he used the potential energy of ATP to create a chemical shock absorber.
A biological field.
Exactly, a shield that sustained quantum entanglement at human body temperature for up to 6 minutes.
And we explored how controlled simulations and magnetic field alignment validated this audacious theory, basically proving that biology might be the missing key to unlocking practical quantum computing.
Which leaves us with a final thought for you to ponder. We are so conditioned to believe that the next world-changing scientific leap will come out of a billion-dollar laboratory, Ro.
Born from massive, isolated academic silos.
Exactly. But if an independent researcher, blending a deep understanding of human physiology from yoga therapy with high-level quantum mechanics, can so elegantly solve one of physics' greatest bottlenecks, what does that say about how we should be looking for answers?
It's a great question.
Perhaps the greatest mysteries of the universe won't be solved by drilling deeper into a single discipline. Maybe the breakthroughs that will redefine our future are hiding in the blind spots between fields, just waiting for someone willing to look at the math from a completely alien perspective.